Welcome back, my friends, and we are still in logarithmic functions, and this is a continuation of the last lecture entitled Graphing Logarithmic Functions, Part 1. So in this example, we are about to graph the log, or the log function log to the base 2 of x squared minus 1. So in this case, because our logarithm now has a base which is numerically not 10, or this is not a common logarithm, then we are going to use the change of base property for logarithmic function. And the base or the change of base property indicates changing the base to a common logarithm, so meaning our base now would be equal to 10. And this could be transformed to the base 10 logarithm by having the argument into the base 10, so log of x squared minus 1, and dividing it by the log of a constant, which is log 2. And therefore, we could now proceed to the graphing of the function, the given function. So I have already prepared here the table. Okay, this is our table of values for x and for our f of x. And our f of x is this one. Okay, so suppose that my x values are from 0, 1, 2, 3, 4, 5, 6. Okay, these are values according to it's your own choice, but you also have to consider the trend or behavior of the logarithmic functions. So we are going to get the behavior of this function, which is already transformed into this function here, by getting x values and obtaining the y values corresponding to the given x values. So when my x is equal to 0, we just substitute the value here. So log of 0 would be, or when our x is equal to 0, that gives us log of x squared minus 1, so 0 minus 1, so log of negative 1, which is, of course, that does not exist. So this is DNA. Okay, and divided by 2 still does not exist. So when x is equal to 1, that gives us log of 0, which still does not exist. Okay, now if our x is equal to 2, then we would have log of x squared, so 2 squared, that's 4 minus 1, so log of 3. Now we have, for sure, a positive value divided by log of 2. So this is 1.585, rounded off to the nearest thousands. If my x is 3, so if my x is 3, that would be 9 minus 1, so log of 8 over log of 2. So log 8 divided by log 2. And that will give me 3. So when x is 3, log is also log of the function is also 3. Okay, which makes sense because in this case, if our x is equal to 3, that's 3 squared minus 1 is 8, and log of base 2 to the 8 is 3. So now let me have my log of x, or my x is equal to 4. So that's log of 15 divided by log of 2, and this will give me 3.907. When my x is 5, so that's 24, log 24 divided by log of 2 gives me 4.585. And when my x is 6, that gives me 35 log of 35 divided by log of 2. So that will give me 5.129. Okay? So I have prepared the graph, and this is the graph. Okay? So as you can see, at this point, at the point here, okay, now let me do it in this case, okay. So at this point here, okay, at this point here, from x is equal to here, and here, okay, and which is, that's actually x is equal to this is x is equal to 1, and this is x is equal to -1. We have two asymptotes here. We have x is equal to 1 and x is equal to -1. Of course, we also have this two y-intercept or two x-intercepts. And what are those intercepts? We have this and this. Okay, and if we want to get our x-intercepts, we set y equals 0, and then we solve for x. So maybe we can do that for now. Let's set our y to 0. So that leaves us with 0 is equal to log 2 x squared minus 1. And this will give us 2 raised to 0 is equal to log, or this will give us x squared minus 1. And 2 raised to 0 is 1. And so we transpose this here. So 1 plus 1 equals x squared. I would like to rearrange my the positions of my terms. So x squared is equal to 2. And x is equal to positive or negative square root of 2. And that's approximately, if we want to get the square root, so we have 2 square root, it's 1.414 or 1.41. Okay, so this is approximately positive or negative 1.41. So this x-intercepts here is x is equal to, let us put it in points. So this is 1.41, 0, and this is negative 1.41, 0. Okay, so this is the graph of my logarithmic function, log to the base 2 x squared minus 1, which can be transformed into the form, common logarithmic form, log x squared minus 1 over log of 2, yielding the same results. So now we would like to get the domains of this function. So let's begin with the first graph that we did. The first graph is a logarithmic function having an x-intercept at 2 and an asymptote at x is equal to 1. So the domain of this graph, okay, the domain of this graph is from 1 to positive infinity, or in the algebraic term, this is greater than 1. Okay, that is the domain of this function. Now let's go to the next function. Our next function is a natural logarithmic function having this graph, this graph. Okay? And so the domain of this is taken at the point when the asymptote is taken. So this graph here approaches our x is equal to -3, increasingly positive, but will not approach our x is equal to -3. And so the domain of this function would be limited. So it would be limited from, so the domain would be from -3 to infinity, or in the algebraic term, this would be x is greater than -3. So this is our domain. Okay? While the last one has a seemingly different type of domain. As you can see, the graph has two curves, one to the right and one to the left. And these two curves define the function log 2 x squared minus 1. Okay? The domain of this graph is located for this portion here, for the right portion. The domain is simply from 1 to infinity, while on the right side it is from -1, or from -infinity rather, to -1. So therefore, in logarithmic or in algebraic standards, our domain is x greater than 1 or x is less than -1. Okay? So this satisfies our problem for example number 2. Okay, now we've got some problem sets to do. These are extra problems. Okay, so we only have 2 problems. For problems 1 and 2, letter A, show that the values in the table have the multiply add property. So this multiply add property is distinct for logarithmic functions. Use the first and last points to find algebraically the particular equation of the natural logarithmic function that fits the points. And letter C, show that the equation in part B gives the other points in the table. So let's do letter A. For number 1, show that the values in the table have the multiply add property. So first, we have to distinguish the multiply add property by getting the specific values or factors or units that define this property. So for the left side, for the x values, we have 3.6 going to 14.4. We could say that by multiplying or by dividing 3.6 from 14.4, so 14.4 divided by 3.6 gives us 4. So this is multiplied by 4. Now let's see if the next value, which is 57.6, gives us the same result. So 57.6 divided by 14.4 also gives us 4. And succeedingly, 230.4 divided by 57.6 gives us 4. And 921.6, so 921.6 divided by 230.4 is equal to 4 also. Now let us investigate the right side of the graph. This is 1 going to 2, so this is plus 1. Okay, obviously these are all plus 1 units. Okay, so therefore number 1 for letter A is verified. Okay, what about for number 2? Let's do number 2. So let's check on number 2 for letter A. So this is by using mental math, this is multiplied by 10, this is multiplied by 10 again, this is multiplied by 10 again, and this is 2, 3, 4, 5. They are added 1 unit. Okay, so 2 is adds 1 equals 3, 3 added to 1 equals 4, and 4 plus 1 equals 5. So therefore, this also has the multiply add property. So therefore, both of them satisfy letter A. Letter B, use the first and last points to find algebraically the particular equation of the natural logarithmic function that fits the points. So for letter B, let us use some containments. Okay, so this is letter B for number 1. Let's do number 1. So 1B. Okay. The first point is 3.6. And 1. And the last point is 921.6. And 5. And the standard for the equation of the general form of the logarithmic function equation is, now we have a natural logarithm. Okay, so y is equal to a plus b ln of x. So therefore, we are going to attempt to get two equations. So the first one, we have the point 3.61, so 1 equals a plus b ln of 3.6, or yes, okay. And number 2, we have 5 is equal to a plus b times ln of 921.6. Okay. So solving the equations by means of subtraction, then this equation here, this is number 2, and this is 1. So 2 minus 1 gives us, it will give me, so this is 4 is equal to a, this will be cancelled, b ln of 92 or 921.6 minus b ln of 3.6, and 4 is equal to b times ln of 921.6 minus ln 3.6, and my b will give me 4 divided by ln of 921.6 minus ln of 3.6, and this will give me, if our b is equal to, okay, let us have the calculator now, calculating, so 4 divided by ln of 921.6 minus ln of 3. So this will give me 0.69888. Okay, wait, I have something here, 83, like that. Okay, so therefore, what we're going to do next is to substitute this value of b to equation 1. It could be equation 1, it could be equation 2, so it depends on what your type is to deal with, your b. So I'm going to substitute this b to equation 1, and therefore I will have 1 is equal to a plus b, and my b is, I have my b, so 0.6983 ln of 3.6, and my a is equal to 1 minus this, because we will transform this product here to the left side. So a will be 1 minus this portion. Okay, so 0.6983 times ln of 3.6. So ln of 3.6 equals minus 1 equals, so we have 0.1054. Okay, so my equation now is equal to what is my equation? My equation is f of x is equal to, my a is 0.1054, okay, plus b. I'm going to move this and expand it a little bit. Okay, so plus 0.6983 ln of 3.6. Okay, or ln of x. Okay, so this is my equation. Okay, next, so we've done 1b, and for 1c, let's do it here on the other portion. So we have so for letter C, okay, show that the equation in part B gives the other points in the table. Let's choose point number 2 or point 2, okay? So 14.4, 2. Okay, using this equation. Okay, when my x is 14.4, so f of 14.4, is it equal to 2? Okay, approximately equal to 2. So I have 0.1054. So let's all have calculator. Okay, with us 0.1054 plus 0.6983 ln of, what is our x? 14.4. What is the value? The value is 1.9679, which is approximately equal to 2. So therefore, this, because our value here is very close to the given y value, the obtained y value here, then this confirms that the equation, our equation here, gives the point 14.42 in this table. Okay, so we confirm this. Okay, now we're going to deal with number 2. So we're going to do it on the next slide. So we are in 2b, and 2b asks us to use the first and last points to find algebraically the particular equation of the natural log function that fits the points. And what is our first and last points? My first point is 1, 2. And my last point is 1005. So again, using the general formula for the logarithmic function is equal to a plus b ln of x. This is for the natural logarithm. Okay, so we would definitely want to find two equations with two unknowns. So in this case, we have, if our y is 2, so 2 is equal to a plus b ln of 1. And for number 2, or for the second point, we have 5 is equal to a plus b ln of 1000. And using again our method to get rid of the other unknown, we will subtract equation 1 from equation 2. So giving us 1 and 2, so 2 minus 1. This will give me, okay, so 5 minus 2 is 3. So I will have 3 is equal to, this will cancel. We have b ln of 1000 minus b ln of 1. And ln of 1 is 0 according to the property of the natural logarithm. So we will be left with 3 is equal to b ln of 1000 minus b. Therefore, we have 3 is equal to b ln of 1000 minus 1. Okay, so computing for b, my b now would be, b is equal to 3 over ln of 1000 minus 1. And that will give me 3 divided by, so 3 divided by ln of 1000 minus 1 equals 0.5. Okay, let me make it more clear. So 0.5078. Okay, and what else do I need to get? I need to get my a. So I would go back to equation 1. And equation 1 gives me 2 is equal to a plus my b is 0.5078 ln of 1, or that's just 0. But I think we made some mistake here. Yeah, we did. Okay, ln of 1 is 0, so this will be 0. Okay, I'm sorry for that. We have to redo some of the computations. So this will become b ln of 1000 minus 0. And so these other succeeding methods would also change. So this will become b ln of 100 only. Okay? Or b ln of 1000. And therefore, we don't need this 1 here. So we would get rid of this. So it will become 3 over ln of 1000. Okay. And our b is, therefore, what is our b? Our b is 3 over ln of 1000. So that would be 3 over ln 1000. So that would be 0.4342. Okay, so therefore our equation for 1, because we want to get a, would be 2 equals a plus 0.434 ln of 1. Okay, and this ln of 1 again is 0, so be careful. So this is 0. So our a is equal to 2. Okay, a is equal to 2. And so this will give me the final equation of, what is my final equation? My final equation would be f of x is equal to, my a is 2, and my b is 0.4342 ln of x. So let us verify this by getting points on the given equation or on the given table. Okay, so let us get a point on the table, and then let us see if this equation works. If this equation doesn't work, then there is something wrong, or we did some mistakes in other steps that we get in there. Okay, so let us say I get the second point, 10 and 3. So 10, 3. So if my x is 10, my y is 3. So let me see. F of 10. This will give me 2 plus 0.4342 ln of 10. So this will be f of 10 is equal to 2 plus 1. So 0.4342, etc. gives us actually a value of 3. So because we have f of 10 is equal to 3, we now verify that the formula or the equation that we got, okay, is correct. So therefore, this is the complete solution for number 2, problem number 2. And this is the end of our lecture for lesson 2-6. And thank you for your time watching and listening. Have a nice day, everyone. So on the next lecture, we're going to do lesson 7.